Okay, thank you everybody for being here. We're presenting today Dr. Nethali Fernando from University of Virginia, and she's going to talk about identifying graph-derived features of trained neural networks via machine learning. Thank you, and go ahead.
Yeah, thank you. So thanks for inviting me. I am super excited to share with you some of the research work that I've been doing for the past few months. Actually, the results have been a lot more improved since I gave my abstract. So let's go. So this is actually, let me take this off. This is actually work with my postdoc PI, who is Dr. Pedro Maya from the University of Texas at Arlington. So let me give you a small introduction to my project. So what we're doing here is that we're using 9 signals, and we're trying to train to recreate these 9 signals through a code called full force. So the description about this code that we're using, this is a third-party work. So this reference is given to you at the bottom, and I'll show you the paper, but I do not intend to go through this code with you. And what we basically do is we try to get the adjacency matrices of these trained networks and extract their graph features using a wrapper that was created by us. So for each signal that we're trying to recreate through this full force chord, we have also created 25 versions for each signal. And how they're created is by adding a Gaussian noise to our original signal. Now, the goal of this project is to classify the signals and their noisy versions using the graph metrics of our trained networks. So this is the full force paper that we're using, and the leaders in this paper is Brian de Pasquale and L.F. Abbott. So visually, to give you an idea as to how this is working, so we have our target signal. All of the signals that we're using are sinusoidal. We have our target signal. We send it through the full force network. And then what we're trying to do is we try to recreate the signal. So you can see the output is in red and the target in blue. So it is pretty good at recreating this signal. And as it recreates the signal, the network is learning how to recreate this, and it changes its network to recreate this. And that's the adjacency matrices that we do collect. And for this particular project, we're looking at the final trained metrics. So the 9 signals that we're using here are these. And throughout my project, I try to use the same colors, the color coding for the different signals. Yeah, and if you actually look at this, if you wanted to see how close or different these signals are to each other, what you can do is you can project them using multidimensional scaling. So this is kind of in the line of PCA, TSNE, if you know that. So through MTS, I just plotted these signals, as you can see. So these are the 9 signals, and there are 25 noisy versions of them. And I did a 2-dimensional plot here, and as you can see, the signals, the clusters are quite far from each other, whereas the 25 versions of the same signal, they are close to each other. So the signals that I have picked are actually quite good. So I had to play with, some of the signals to make sure they are distant from each other. Throughout our project, so we use Python and Network X. This is network analysis in Python is what we're using. So basically what I'm showing you here is directly from the page of Network X. And if you can remember, I told you about a wrapper that I use in the pre-processing of these matrices, and network X is used heavily in my wrapper. All of the network metrics are coming through this network X's network metrics. So before we start with anything, we got to pre-process the adjacency matrices that we get from the full force chord. So how do we do this? If you actually look at all the matrices, they look pretty much the same because of the small world characteristics. So if they all look the same, obviously the classification problem is not going to be that's much successful because it's hard to distinguish between the matrices. So we had to come up with a way to discriminate these matrices who look pretty much the same. And the way that we interpret these things, so in our metrics, we would have numbers that are positive, negative, and 0. And the positive entries, we think of this as the excitatory links. So in a more neuronal network, biological network sense, these are the links that promotes or generates an actual potential. And similarly, the negative entries, we try to describe them or think of them as inhibitory links in a biological network. And these are the links that inhibits the generation of an action potential. So what we do now is we want to keep the strong links and discard the weak links to differentiate our networks. And to do this, what we did was we took the absolute value of our matrix, and then we removed all of the links that were smaller than mean plus 1 standard deviation. Now, when we do this, there's a problem. So we start off with our network that is connected, but when we try to remove the links, we could end up with a disconnected network. So in order to make sure that our network is not disconnected, because why? If the network is disconnected, most of the graph metrics coming from network X will not work. So we needed to make sure that in order to be able to use the graph metrics of network X, that we keep or preserve our network connected. So what we did was, again, coming from network X, there is this function called k-edge augmentation. And the k value that we use is 1. And what we basically do with this is we make sure that in case if our network gets disconnected, as shown in this picture, if we remove this one link, now our matrix is disconnected, but with k equals 1, we're just, reconnecting this network, meaning if you remove one link, again, our network will get disconnected. So we are connecting it again, but we're doing it minimally to make sure that it is not very different from what we started off with. But as you can see in the picture, in doing so, we may create new links that were not there to begin with. There's a question. Should we take the questions later or? Okay, I guess I would like to take the questions later. So
As you prefer, as you prefer.
If somebody can tell me the question, I think that would be great. So I don't have to go back and forth.
Yeah, the question is, will network X work only with connected graph, or you can use the connected components on network X?
Yeah, so for most of the metrics that I used, we do need the connectivity. But there might be, metrics that you can use for not connected graphs. The majority needs that connectivity.
Sounds good, thank you.
Mm-hmm. Yeah, please do let me know if there are questions. I think I'd like that. Okay, so let me show you what the train matrices look like. So here is actually for my first signal. So it starts off with a matrix that looks like the first one. So in here, the blue dots are the positive components, and the green is supposed to be negative, and the whites are just zeros. So as you can see, they are different, right? As they train, like these are 3 snapshots right at the beginning, somewhere while it's getting trained, and then at the end, once it's trained. So they are different from each other. And this is actually for all of the 9 signals. If you look at them, yes, at different snapshots, they're different, but also going from signal to signal, also they're different. It might be a little bit hard to see, right? But they are different. So that means our networks are learning, and we have now these different matrices. So for the metrics, okay, how do I remove this? Okay, I'm sorry. So for the metrics pre-processing, what we do is first we take our original metrics, and then we remove the self loops again, because for some of the metrics, this self loop will inhibit from working. So remove the self loops, and then we do this thresholding that I spoke to you about earlier, where you take mean plus 1 standard deviation and then remove the lengths that are smaller than that. And then once we have done that, we look at 3 different matrices, which we call the absolute value, or ABS, then excitatory and inhibitory. So basically, once we take the thresholded metrics, what we do is if we take just the absolute value of that matrix, that's what we call the absolute value. And then if we just take from the threshold just the positive entries, then that is your excitatory matrix. So everything else is 0. The negative values would be made 0. And the opposite is done to create the inhibitory matrix, where you take the thresholded matrix, but now what you do is you are going to remove all the positive entries, and you're going to keep the negative entries. But then again, you're going to take the absolute value of that matrix, because now that you know it's inhibitory links, you don't need to have the negative sign anymore. And once we have this, we go ahead and we do, we find the average absolute value and the binary absolute value, for example, in the absolute value. So for the binary, what you do is now the absolute metrics, what you have is going to have these different values. But if we wanted to make it binarized, right? So all the values are going to be 1, right? That's where we're going to have, like, whenever we have a value, we're just going to make it 1. That's your binary absolute value. And the average absolute value, what we do is we take the strength of the links, like compared to a couple of nodes. So if you have 2 nodes, if you have a link going from A to B and B to A, the average strength of that link would be what we're going to assign to that link. So in a way, it's going to symmetrize this particular matrix. And finally, we have the filtered binarized absolute. So what we do here is once we have the binarized, actually, give me a minute. So this one is, sorry. So for the average absolute value, this is going to still be weighted, because you can see the weight, but it's going to be undirected because we symmetrize it, and it is going to be unsigned. And for the unweighted, for the binarized absolute values, it's going to be unweighted, because now we've taken the weight off, and it's going to be directed and unsigned. And finally, we create an unweighted, undirected, unsigned matrix by filtering them in the final step. So basically what we do is we take the matrices, and then we look at these different variations of the same matrix, but we're doing only one classification problem. So we're creating a whole area of classification matrices by just changing the metrics, how we're looking at it. So depending on that, so whether I'm looking at, the full network right at the beginning, the threshold, or some of the other subnetworks, or I can also look at the mixed networks where, for example, I can look at all the absolute value matrices or the excitatory or inhibitory. So those are the mixed networks. So by looking at that, we actually end up having 12, 15, 16, right? Yeah, problems altogether. And all of these would start with a high number of features coming from network X, but not all of these features will survive till the end. For example, it could be the case that for, say, the absolute metrics, maybe 3 of the columns, right, 3 of my features, they have the same value. So in that case, it's not going to help us to differentiate these different signals. So taking a little reroute, there is something called lazy predict. I don't know if you have heard about this, but this is actually a really cool tool. This was introduced by Sankar Pandala in 2021. And what this does is that, so usually when we do a particular classification autoregression problem, we have our data set, and then we do all the pre-processing, the data curation, and then we have to plug in different models one at a time to check, for example, the linear SVC or a SGD classifier in the classification problems. You do one by one and then evaluate how well it works, right? Each of these models in order to pick up one model. But what lazy predict does is once you only have to give your data once, and then it has this assortment of different classifiers and regresses, again, coming from Python's scikit-learn. And it'll go through all of these models at once and give you a evaluation of how well it does with all of these different models. So it's quite efficient and automatically tests like 42 odd regresses and 32 odd classifiers. So that is helpful. So we knew about this, and we actually do use this in our projects, and the graph metrics wrapper that was created in our lab was inspired by this. So this, checks an assortment of different models, whereas in the wrapper that was created by us, we check an assortment of graph metrics coming from network X. So that is that. And then let's walk through the pipeline. So basically what we first do is we have to train the signals using the full force chord, and then we have to save the weight matrices or the trained matrices. And then for feature extraction, we use the metrics extracting wrapper that was created by us, that was inspired by lazy predict. And then at the data curation stage, we pre-process the weight matrices. So in here, like I said earlier, if we see that a particular column is not changing at all, like the whole feature, the whole column has the same number, then there's no point of having it as a feature. We remove that. And also if there's a column where we could not really calculate a lot of data and is missing a lot of data, we don't want to go and impute that. So we remove columns that are like 40, doesn't have like 40% of its data or more. If it's missing that much of data, we remove those columns. So there's a little bit of pre-processing in that way, and also about the pre-processing that I spoke earlier, where we have to do the thresholding, removing the self loops, and things like that. So once we have done that, finally, now we're ready to impute, and this is where we try to come up with we try to fill in the missing data. And what we have agreed to use is the K-neighbors imputer. This is again coming from sklearn, and we impute when we try to impute these numbers, we impute per signal. So we only look at when I want to fill in the blanks of a particular signal. I only look at that signal's behavior, not behavior throughout all of the signals and its versions. And when it comes to data standardization, again, we use the min-max scaler to scale it. And then the standardization is also done per signal. And then for feature sorting, we use lasso loss and archaic information criteria. I'll show you this in a minute. And then for feature and method selection, so which features am I going to use, which method, classifier method I'm going to use. I'm going to use lazy predict wrapper to help me with that. I'm going to show you that also a little bit detailed later. And then finally, we do hyperparameter tuning to optimize our parameters. So about feature sorting, so we used lasso loss with AIC, archaic information criteria. If you do not know that, it's basically helping you to, if you have two models and you want to pick one, the AIC. So AIC is a value, and the model with the lower AIC is the better model. So this is what we use to basically get the coefficients, right, of our problem, which are like our features. We want to rank them first using this criteria. And once the way we rank them is by looking at the absolute values of these feature coefficients after we run it through lasso loss with AIC. And if you have high coefficients, it doesn't matter whether it's positive or negative, right? That means there is a high correlationship between those two. So that's why we look at the absolute values, and then we order them in the decreasing order. Ones that have the highest coefficients, we'll give them priority. And that's how we sort out our features. So once we sort out the features, then what we do is we have to find a good model that does the, classifying problem, the best. So what we do here is that we take a subset of features now that we have them sorted. So we start off first with, one feature, two feature, three feature, like so, starting with the best ones. We take all of these subsets, and then we run the lazy predict wrapper 5 times. So why we have to run this 5 times is because every time we run the lazy predict, it has one train and test set. So depending on, when you run it one time and the second time, when the train and test splitting is different, you can get different, quite comparable, but could be fairly different results. So to make sure that we are consistent, we run this 5 times and we look at the mean values, mean of the balanced accuracy. So why the balanced accuracy? Because our data set is not balanced. And then also we look at the lowest mean AIC value. So this would help us to avoid overfitting. So once we have that, so this is a snapshot of how the feature metrics would look like. And these are the columns that I've been telling you about. So we have both categorical and numerical data. So going back to the results now. So our best classifier results are coming from the subnetwork level, and that is in our problem CS5, which is our average excitatory metrics. So we start off with 31 non-zero features after cleaning up all of the features. And after going through this feature sorting and using lazy predict, we ended up with 5 features. And this gives us a balanced accuracy of 0.85 and an AIC of -1018. So yeah, that is actually our second best. Our first best is in yellow, sorry. So our first best would be CS9, binary inhibit, and that is a 0.92. So I think in my abstract at that level, we were in the 70s, and now our balanced accuracy is in the 90s. So we have improved, our results quite a bit. Yeah, and the AIC also helps us to compare these different models. So definitely CS9 seems to be doing quite better than CS5, but these are runners up, the first and the second. What would be the question? Yeah, I'll be happy to take the question.
Okay, if you want to see the questions, I think you can hit in the Q&A, but I'm
Yeah,
gonna, yeah, so it says, do we have a certain number of features to be chosen in our models? How do we decide how many top ranked features to choose?
yeah, that's an excellent question, right? So as you can see, we start off like around 30, right? But the thing is, it's you want to come up with a number of features that make sense in your context. So in my problem here, features are the main driving resource here. Like I really, as you can see, the classification problem, the classifying, it seems to be good. Like I started off at 70, now I'm at 92. But what I want to say is, what are the features that can actually discriminate this or classify, these different signals, or in a way, which features are actually encoding this information. So if I have like 30 features, it's now very helpful to say, hey, yeah, I mean, training is good. And if you really wanted to check, for example, a baby's brain who's still learning, you have to check all these 30 features in order to see if they have understood something or not. That's not very helpful. So I have to reduce it. And in my case, like in my second problem, I only have 5. With 5 features, I can give a balanced accuracy of 85. And in my first, my winner, I could reduce it to 12 and 92. So it's you can be as stringent, as possible, maybe like, um, by increasing, saying, okay, I'm still not happy with this AIC. I'm going to try to, be more strict about it, or play with the lasso loss in my case to come up with higher penalty so that we reduce it. But there's always this balance of when you try to reduce the features, your balanced accuracy will also suffer because you're trying to explain. These are like two opposing things, right? So the more features you have, right, better your balanced accuracy is going to be, because every variation is now being explained by all of these different features. So it's always a balance between these two, but I think it depends on your context. Like 12 still might be too much in some contexts, maybe, but I still do not know that. At the moment, we're happy with this balance. But I think it's quite specific to your what you want to do. Yeah, I hope that makes sense. Yeah, it's always difficult. Yeah.
I have a question now that we're talking about context. So how overfitting looks in this scenario?
Yeah, so that again, I guess it's very much linked to the previous question, right?
Yeah.
So I guess in this problem, one good indicator would be, your balanced accuracy. Like for example, if you're like over like 98 or something, definitely that could be a good indicator for overfitting. But as you can see, I only have like one problem with in the 90s, and everything else is in the 80s and the 75s. So I would say, and also given the nature of my problem, I'm not giving a really hard classification problem here. the signals are quite distinct, as I showed you earlier, right? So, and in our models, we have things like perceptrons and even linear discriminant analysis, as you can see, are the winners here. The best classifiers are quadratic discriminant analysis, which are not very sophisticated models per se, right? So with very quite simple models, I've been able to achieve a high balanced accuracy, which gives me the indication that this problem, the classification problem, is not the hardest problem to solve, correct? But what I'm interested in is actually the encoding part of it. So these features, who are these features that are encoding this different the signatures of my signals? That's what I'm interested in. So for the moment, I am happy with what I have, and I think this does not involve any hopefully any overfitting, but it is something to definitely to ponder about.
Thank you.
Mhm. So the same observations, if I rearrange them, the absolute excitatory and inhibitory, looking at, the original, when we take the average, when we binarize, and when we filter. So what we're trying to think is, okay, so we have these matrices, but how should we pre-process these matrices in the future to get the maximum out of it, right? So as you can see here, and so when we look at the absolute value metrics, this seems to be the least useful. It is not helping, probably because in the absolute value, you have both the excitatory and the inhibitory all mixed together. And now we cannot, tell our signals apart using this. So this is definitely absolute value metrics is a loser compared to the excitatory and inhibitory. Averaging actually helped us in the absolute and the excitatory, but not in inhibitory. And binarizing helped in pretty much all of them. So that seems to be like a good strategy going forward. And then filtering only helped in the inhibitory. So it's kind of also interesting how, even though the excitatory and inhibitory is just a plus and a minus, they're still, so like maybe averaging works better in excitatory, but not inhibitory, vice versa, right? They're still very different. And then actually going back to, the main, features, what we've been looking at, what are the features that are very important? We're still working on that, right? So in here, I've taken the best two problems, the first and the second problem that I showed you, the winners, which is CS5 and CS9. CS9 had a balanced accuracy of 0.92 and CS5 had a balanced accuracy of 0.85. And we're just, still at the stage where we're comparing these features to see which ones are more important. And in here, what we see is in both of these, we see this closeness, centrality, and effective size coming up. So definitely, these two features seems to be important. And if you look at average inhibit and the inhibitory metrics, the inhibitory is the winner. And they both have this highlighted features. So the unhighlighted features on the right of the winner, like for example, the average shortest path length or the edge between the centrality, this seems to be, what differentiated from, CS6 to go from CS6 to, go from 64 to 81. Balanced accuracy, we're guessing it's these features that helped. So these features that are not highlighted on the right should be more important. So there's a lot of centrality metrics that comes up. And we did the same with CS3 and CS9, where CS3 is inhibitory metrics with a balanced accuracy of 8.1, and CS9, which is our winner, has binary inhibit with a balanced accuracy 9.2. Again, if I highlight the common features, what helped us to go from 81 to 92 should be effective size, communicability between a centrality, graph number of clicks, and information centrality. And finally, these are like, if I take all of the features that were selected in different problems, and every time they got selected, if I give them a score of 1, this is the most picked up features. So closeness centrality is on the lead, then core number, average clustering as metrics, degree centrality, edge between a centrality, communicability between a centrality. So a lot of centrality measures. And finally, if I draw a MDS plot for signals in my feature space for not the winner, but the second best problem, it would look like this, right? So if I take the features and then plot, using MDS 2D plot, it would look like this. Looks like a bit messy, even though our classification results were good. But if you actually try to look at a pairwise signals, like so here I have the 1 and 3, then you can see, yeah, there is a good separation between those two. So yeah, that's all I have for you for today. Thank you. I'll be happy to take any questions.
Well, thank you so much for that. So
There's
we have a
another
question.
Yeah.
Yeah. So we have a question here. How does Lazy Predict choose the regressor and classifier? Are all 42 regressions in R32 classifier fixed?
Yeah, so these are actually classifiers and regressors coming from the scikit-learn, but for your given data, some of the classifiers might not work, some of the regressors might not work. But on average, the assortment has this number of classifiers and regressors.
Sounds good. One other question. For the model selection, is the AAC working in the same way that the R-squared will work for checking the fit and generalized linear models?
For the model selection, is the AIC working the same way? R-squared. I guess the flavor is the same, but definitely the theory is different. You might want to look into the AIC framework. So there's two that are very close, AIC and BIC. AIC is the archaic information criteria, and Bayesian information criteria, BIC. Go ahead.
I also probably don't have an idea of what the AAC entails in detail.
Yeah, I would invite you to look at it. It's I forgot, but it's to do with likelihood and the formula. Yeah, just have a look at it. But the flavor is the same. Yeah.
Underlying idea.
Yeah, the underlying idea is the same.
Any of you guys have any questions?
My question is about the AIC, but it was just what it was.
What it was specifically, the AAC?
Okay, we can pull it up.
I was about to say, I think you said the police.
Yeah.
Yeah, I didn't know about network X either. Like I work a little bit about, I do stuff with graph theory, but more like putting differential equations on them. So I'm kind of curious now.
About network X, you said?
Yeah.
Oh, that's really cool. Yeah, I do everything there. It's very useful. Okay, so yes. So the archaic information criterion is 2k minus 2 times ln of L. So k is the number of model parameters, and L is the maximum value of the likelihood function of the model. So basically what it does is, the idea is every time you try to add a feature, because the more features that you add, the better your accuracy is going to be, right? So what this does is every time you try to add a new feature, it'll penalize you. That's what it does. Yeah. And the Bayesian criteria also does a similar thing. BIC. The two formulas are, I think, a little bit different. That's the difference. But you can use either. And on sklearn, they already have these things incorporated. So if you want to use them.
Very interesting.
Mm-hmm. For lazy predict, they don't have, but I had to, create a little snippet, and I added it to lazy predict. So I have my own version of lazy predict where I have AIC also. So I can compare my models. But you are welcome to go and check on lazy predict. I mean, it's really cool. I will share my slides, and you can have a look at them.
Yeah, it was pretty interesting.
Yes.
And like the number of like the different regressors and the classifiers that you have, like they are fixed. Like
Yeah. It's
so
not
there
the
is some
best.
threshold that you can just like change them and decide to go with small, like more or less.
So
or they have a pool of like classifiers.
can you ask that question again?
So I'm like in this the lazy predict model that you said. So it has full of classifiers and regressors that already have chosen, and they are available. So it looks like checks all of them.
Exactly.
The accuracy and how much time they take.
Yes. So there's an ensembler, in scikit-learn, and he takes Sankar takes a lot of these ones. Some of them are problematic to calculate, so he removes those, and the ones that are easy to calculate, he has created them in here, like added them to the basket. And yeah, it's pretty neat. And also if you wanted to like add the AIC into your lazy predict, it's not very difficult. The only thing though that lazy predict does not do now is hyperparameter optimization. You just have to use the default parameters that comes with scikit-learn, because I mean it's already doing a lot for you, but I think at some point they might be right. They might be able to. I did speak about this with Sankar.
That is what I asked. Like hyperparameters. One of them can be how many regressors.
Exactly. Yeah.
Okay.
So at the moment, I mean, it's already doing a very good thing for us. Like it gives me an idea of, who are the best classifiers to start off with. And once I have picked up my features and the best classifier, then I can go ahead and manually like optimize it. That's what I do, which is still crude. Otherwise, I would have had to do that manually for each and everybody. But now, yeah.
Awesome. So let's thank our speaker. Great help. Thank you so much for your time.
Yeah, thank you for inviting me.
Questions? Any other questions? Let us know. So like either like in the chat. Okay.
Yeah, I mean, if you have any questions later too, you can ask Dr. Ingefard, and she can send me the questions. I'll be more than happy to answer.
Thank you.
Mhm.
All right, thank you.